In this lecture, we're going to examine an event called the action potential. And the action potential is the mode of communication that muscle cells or neurons use in response to graded potentials and as a means of transmitting a message from one cell to another. And the action potential is initiated by what's called a depolarizing current. And when that depolarizing current achieves the threshold, then that will cause an increase in the flow of sodium ions into the cell. And this is referred to as the current. And the mode in which these sodium ions can move into the cell is through ion specific channels for this particular ion, being sodium. And the next question of how the sodium channels open is that the sodium channels open either through a chemical stimulus or an electrical stimulus. And what happens during the course of the action potential is that we see a very large deflection in the membrane potential. The membrane potential changes from more electronegative on the inside with respect to the outside of the cell to a positive state. So if our resting membrane potential in this example here is negative 70 millivolts inside with respect to outside, and recall that this resting membrane potential value can vary a little bit, sometimes as low as negative 80, oftentimes closer to negative 60. But the action potential will see that change to a value of plus 30. And this happens very quickly. And very quickly, it means that it happens within 1 to 2 milliseconds. And this is typical of neurons and skeletal muscle cells. To contrast a different type of cell, cardiac muscle cells will hold those action potentials for up to a half second. So these are much longer action potentials generated in cardiac muscle cells. But when we look at neurons and skeletal muscle cells, the action potential occurs over a much shorter time frame. And we use this graph to illustrate the time course of these physiological events within the action potential. So along the y-axis is our measurement of membrane potential in millivolts. And if we start with a resting membrane potential of minus 60, recall that if we provide a stimulus to a neuron, and what we see here along the bottom is we provide more and more stimuli. And what's notable here is that the stimuli here are occurring in closer time proximity. So the frequency of these stimuli, as you can see, increases and it compresses in time. And if we only have the one stimulus that generated this action potential, and then we activate it again before the cell membrane potential goes back to its resting state of negative 60, we can see that the resting membrane potential will eventually decay to the threshold. And if the inward current, and so when we talk about the inward current, we are adding positives to the negative 60 to make it closer to, for example, negative 55. And those positives are in the form of sodium ions that are moving towards the interior of the cell. And then once the threshold is achieved, then we see this very, very fast deflection in the positive direction. And usually this occurs up to approximately 30 millivolts. At the very top, at this very peak, that is referred to as the depolarized state. The process in getting to the depolarized state is just simply referred to as a depolarization, or a movement away from the polarized state of negative 60. in the depolarized state at the very top, the sodium channels have closed. So recall at the very bottom here, the sodium channels have opened considerably more than they did here during the red graded potential. And when we have more sodium channels open up, that very short opening, that very short-lived opening is enough to cause enough sodium ions to enter the cell to cause a big deflection up to positive 30. And the depolarized state, this bioelectrical state, which is now positive 30 millivolts on the inside, is the trigger for potassium channels to open. And recall that in the resting state, potassium is kept in greater concentrations inside the cell than outside. So once those potassium channels open, there are two motivations for potassium to leave the cell. The first motivation is the concentration gradient. So as there are more potassium ions inside the cell, when the potassium channels open, that will allow the downhill flow, if you will, downhill in terms of concentration gradient from the interior to the exterior of the cell. And the second motivating factor is that the membrane potential inside with respect to outside has become positive 30, and because potassium is positively charged, these two repel, and that will motivate potassium to leave the cell. So that will result in what's called the repolarization phase, where the potassium will leave the cell, and that occurs here. So as that cell is sitting at positive 30, it is now depolarized, losing positive charges on the inside of the cell will bring it back into the negative direction. And what we see here is that the membrane potential returns back not just to the resting level of negative 60, but it undershoots it on the graph, and it becomes even more negative. And this is called the hyperpolarization phase. So not only is the cell returned to its polarized state, it's even more polarized, hence the term hyperpolarized. And there are some unique phases in what's called in this action potential. So the entire set of events here is just simply referred to as the action potential. We see this region here called the absolute refractory period. And this period we can see lasts between the two threshold points. And so when the cell has hit its threshold during its depolarizing current to the point where it now crosses back in the opposite direction past the threshold, the cell cannot generate another event in this case. The cell has to, at the very least, reset below the threshold before further stimuli can generate another action potential. And once that cell's membrane potential drops below the threshold, that then enters what's called the relative refractory period. Another action potential at this point is very unlikely, but is possible. It's possible, but it does require a stronger stimulus to elicit another action potential. And so when we look at the action potential and divide it up into three distinct phases, the very first phase we see is what's called the rapid depolarization. And this occurs once the cell has hit its threshold. And the depolarization is generated through an increased permeability of the membrane to sodium ions. And since the interior of the cell is resting at a negative level, there's both an electrochemical and a concentration gradient that would drive sodium into the cell. Now, as sodium flows into the cell attempts to reach sodium's Nernst potential of positive 67 millivolts. But the cell does not actually reach positive 67. It stops and actually reverses on the way to 67, but stops at about 30 millivolts. And that's because of the opening of the voltage-gated potassium channels. The movement of the interior of the cell to positive 30 is the voltage stimulus for potassium channels to open, and that occurs at the same time as the sodium channels start to close. And at peak depolarization, the sodium channels have closed, and that's through what's called the inactivation gate. That initiates the next continuous phase of reversal called repolarization, and that's generated by potassium channel opening. So as the potassium channels open, potassium flows down its electrochemical and concentration gradients. So the positive charge of 30 inside the cell is strong enough to repel potassium to leave the cell, which it will do anyways because of the concentration gradient. It just now has a greater motivation, a greater what's called electromotive force to push it out of the cell. So the positive ions will leave the cell, and the cell will start to move from positive 30 back in the direction of the resting membrane potential. So the cytosol now starts to become more negative from the positive 30. And the membrane potential returns to resting values. Not only does it go back to the resting state, but as illustrated on slide number 34, it actually undershoots it into what's called the hyperpolarization phase, sometimes referred to as the after hyperpolarization phase. These terms are used interchangeably. And this occurs after the main events, hence the term after hyperpolarization. And those main events are depolarization and repolarization. And the term hyper indicates that the membrane potential becomes even more polarized. So recall that when we talk about the polarized nature of the cell, it's approximately negative 60 millivolts on the inside with respect to the outside. And if we hyperpolarize it, it's even more negative. And the hyperpolarization phase can last anywhere from 5 to 15 milliseconds. And during the hyperpolarization phase, the neuron can be activated again into another action potential, but it's much more difficult to do that, and it often needs a much stronger stimulus to bring it back to its threshold. So this ends this video on the action potential.